on YouTube. Testing on YouTube. Testing on YouTube. Testing, testing, testing. All right, YouTube works. How's it going? Sankalp Nagaonkar. Wait, but my GitHub link is wrong. This should be the 14th. All right, there we go. All right, now we just need to wait for X to start. Alright, I think X is live. Let's get to it. Let's start it. Alright, welcome to another Hoopo stream. Today we're going into the computer vision world. To look at some Gaussian splatting papers. So it's been a second since we looked at some Gaussian splat papers, and that community has been pushing out all kinds of stuff. So we're going to be reviewing some of the stuff that came out since then. Yeah, so the stream is called LangSplat, Compact 3D, AGG, and then there's also another paper that we're going to be looking at called Spacetime Gaussians. It's going to be harder to kind of like have a single thread that goes through every single one of these because they're a little bit different, but why don't we just start with, I think, the coolest paper, which is this one. This is LangSplat, 3D Language Gaussian Splatting, released on the 26th of December 2023. How's it going, Aries Aurélien? This is joint work from Tsinghua University and Harvard University, which is, you know, I guess pretty interesting, right? That you have basically Chinese and American universities collaborating on AI stuff, you know, despite all the kind of negative talk around AI and geopolitics and separate tech stacks and hardware restrictions and all of that nonsense. You're still seeing papers coming out where you have kind of joint efforts between both nations. So I think that's good to see, you know, kind of want to see everybody come together. So this paper, LangSplat, right, the lang comes from language and then splat comes from the Gaussian splatting, is basically adding language information and semantic information into Gaussian splats. So obviously, they're going to be using CLIP, which is the contrastive language image pre-training. It's basically the source of language features. If you're going to do anything in the image space that has some kind of text language semantics, you're pretty much going to be using CLIP, and this paper kind of does that. But you can see here they have a scene with a bunch of objects on a table. Here, actually, underneath the table, you can see what it looks like when a Gaussian splat doesn't have good coverage. You see how that weird, like almost like misty look. But you can see how here they've kind of segmented out based on language features, and you can see that the boundaries of every single one of these objects is pretty clearly defined. And here it is for this bear sitting on this chair. Some of the boundaries are a little bit fuzzy, as you can see here. Like there's a little bit of weirdness. These aren't like the super clean, crispy segmentation maps because each of these scenes is composed of millions of Gaussian points, and each one of those individual Gaussian points is basically being segmented and then assigned into one of the classes. So you might have just like a little bit of weirdness where you can see here, for example, on the bear's hands, like there's a little individual Gaussian splats that seem to be labeled according to whatever the bright pink is, some other class. But pretty strong results, and I think it's the first one I've seen to do this. So people have done this type of stuff with NeRFs before, and that is called LeRF, and they mentioned that a couple times here. So the main work that they're comparing to is this paper here, LeRF, which basically was this exact thing, using CLIP to kind of do texty, semantic-y things with NeRFs, but NeRFs are pretty much dead at this point. They've been dying. They pretty much died over the course of last year. They were super popular for a specific point in time as the kind of 3D representation of the future, but Gaussian splats have usurped them, and Gaussian splats are now the king. How's it going, Ed? And how's it going, Liu? Dear Hupo, I want to learn C++. Do you have any good person you recommend? Well, first of all, I would say C++ is not, I don't know. I'm someone who, like, some of the C++ was some of the, I used that way back in the day when I was doing more roboticsy type stuff, but then as I've kind of moved more into machine learning, I kind of moved more to Python. And I know Python is slow and C++ is fast, but C++ is really annoying to write, and it's a lot longer to write things. And I feel like the way that technology is moving very, very fast, you want a programming language where you can very quickly prototype things. So yeah, actually the Llama CPP codebase is probably a pretty good place to start if you're interested in that. But yeah, my general advice is that C++ is not like a good kind of beginner-friendly programming language. I would start with Python, and then if you kind of see yourself kind of really in that C++ world, then maybe, or in that programming world, then maybe move to C++ and things like that. But it's going to be harder to find a job, and it's going to be more annoying to build projects in C++. How's it going, Josh? How's it going, Spyro? Is Rabbit R1 legit? Question from SHC. Rabbit R1 is, wow, we're immediately getting distracted here, but it seems like you guys are cool with that. So the Rabbit R1 was this like almost like Tamagotchi type thing that they like announced at, I think it was CES or something like that. But I'm just gonna be honest, I don't really understand what the fuck this is. It's basically just like a cell phone, like a shitty cell phone with an LLM integrated. It's probably not even their LLM. It's probably just OpenAI API. Like, what is the point of this? Right? I don't understand. It's just it's like a $200 like cell phone. I don't know. Like, to me, it's like there's nothing that's going to beat the kind of cell phones that you have now, right? Like, those have been optimized for decades at this point, and the cost, performance, and kind of like package is way too good to compete with. So I don't think it makes any sense to get into the cell phone game in 2024. So I don't understand that. But to me, I think if you're going to try to make a new like hardware platform, you got to go kind of VR AR, because VR AR, there actually is like features that you don't have in cell phones, right? So the kind of like egocentric view, the ability to kind of like spatially render things, that is something new, right? So there is a way for a new AR VR kind of device to beat out a cell phone. But I don't see a way where people are going to beat out a cell phone with this. But I don't know. I don't necessarily want to be a hater, you know? Like, these people, it seems like they got a bunch of pre-orders. So I don't know. Maybe it's successful. Maybe it's not. We'll see. Only time will tell. Rabbit R1 is a boomer bait. Maybe. I think, like, actually part of it, you know, to be honest, is literally, like, humans are very materialist and consumeristic. So, like, there's kind of, like, a weird thing you can exploit where by making this, like, $100 or $200, right, people are willing, that's like right at the boundary level where like the random tech bros who have big salaries anyways, they're just willing to buy it, and they're probably going to play with it for like a month, and then they're just going to throw it away. So like you can leverage that kind of materialist consumer instinct to basically get people to buy novelty hardware, and then even if it breaks down after a month, it's like you still got your money, right? And there's entire industries of this kind of stuff where you basically take some consumer device, you add some kind of meaningless tech to it, and then people buy it, and then it breaks, and it doesn't matter because you already made money off of them. So I don't know. I think this is more along that vein than actually something we will see in the future, right? Like look at this little wheel, like a scroll wheel. Why not just have a touch screen? Like what? Okay. Back to Langsplat though. So Langsplat, if we look here at the abstract, humans live in a 3D world and commonly use natural language to interact with a 3D scene. And I think this is kind of, they're going to be kind of like providing justification as to why this is so cool, but I think that's kind of the beginning motivator there, where imagine you have a Gaussian splat scene and you can basically segment with your voice, right? You're seeing this in your VR headset, you have basically this 3D scene in front of you, and you can say, tell me more about the chair, and it's like the chair, and it highlights both of these chairs, right? So the kind of like interactive spatial 3D world that we're going to want to live in the future, we're going to have to be able to interact with it basically through speech. And in order to do that, you need to have something that kind of adds that text semantic information into each of these little Gaussian splats. So they're calling this a 3D language field, which a field is just basically a function that you can evaluate at a point in space in 3D. So a 3D language field is basically at any point in this Gaussian splat, you can say what is the text word that describes this point in space. To support open-ended language queries has gained increasing traction. This paper introduces Langsplat, which constructs a 3D language field that enables precise and efficient open vocabulary querying within 3D spaces. So basically asking, hey, what is this? Or hey, highlight the milk carton or something like that. Right, that's what open vocabulary querying is. Open vocabulary refers to the fact that in a lot of older works, usually the segmentation or the classification is bounded to a specific set of classes or categories, right? There's like a preset list of categories like ImageNet, right? There's only some limited set there. But in open vocabulary, you can basically use any word. And open vocabulary is pretty common nowadays. For example, the segment anything model is open vocabulary. A lot of the kind of more modern segmentation and classification stuff is open vocabulary because of this bad boy here, the CLIP language embedding. So CLIP is contrastively trained language image. It basically uses captioned images to create this kind of joint embedding space in which you can go from image to language and then language to image. Langsplat advances the field by utilizing a collection of 3D Gaussians, each encoding a language features distilled from CLIP. So each of the 3D Gaussians, right, and the way these 3D Gaussian splats work is it's basically this giant set, right, a giant bag of these little 3D Gaussians, each of which have a bunch of little properties, such as the center of the Gaussian, how wide it is, the color of the Gaussian, and there's a lot of different fancy things that you can add as properties to each of those little Gaussians. And in this paper, one of the little things that they're going to add is they're going to basically add some language features. And they're going to, the distilled here comes, they're going to explain this later, but basically the TLDR is that the CLIP features are quite high dimensional, so adding a 512 dimensional feature vector to every single 3D Gaussian is a little bit memory and memory prohibitive, right? You would just explode the size of your 3D Gaussian set by doing that. So they basically distill these more tiny little language features so that it's not as many numbers. Employing a tile-based splatting technique for rendering language features, we circumvent the costly rendering process inherent in NeRFs. So here they're just shitting on NeRFs a little bit because it's a splat paper. Of course, you gotta shit on the NeRFs. Instead of directly learning clip embeddings, first trains a scene-wise language autoencoder and then learns language features on the scene-specific latent space. This is basically how they're compressing the size of these language features from clip. I'm not necessarily in love with this part of the paper because it just adds extra complexity, but they kind of have to do it to alleviate the memory demands imposed by explicit modeling. Explicit here referring to the actually explicitly storing the clip language feature vector for every single Gaussian. It should be... Can we have 3-minute chill breaks or something midstream? These things sometimes are overwhelming 2-hour sprints. That's the whole point, man. I go fully wired, I get fully caffeinated and then I just blast through the 2 hours. But I'm also someone who only listens to content and podcasts at 2x speed. So I even find it unbearable to listen to my own stuff at 1x speed. So I don't know how you guys do it. Existing methods struggle with imprecise and vague 3D language fields, fail to discern clear boundaries between the objects. This is not as much of a flex as they think it is because their technique also suffers from that. We delve into this issue and propose to learn hierarchical semantics using SAM. So SAM here is referring to this. This is the Segment Anything model from Facebook or Meta. The Segment Anything model is basically the end-all, be-all king of segmentation. It's basically been trained on 11 million images using 1.1 billion masks, and it was trained in such a way that it's also it created its own data. So they trained it on human masks, and then it annotated more masks in other images, and then trained on that. So it's not only is it kind of the largest mask data set that's ever been assembled, but it's also iteratively created its own data to the point where I don't think anybody's going to beat this segmentation model for quite some time. And not that anybody would want to, right? It's pretty much good at everything. And the way the segmentation model works is that you can prompt it with a variety of different things. So you can prompt it with points, you can prompt it with boxes, or you can prompt it with text. So you can see here how this little green dot, what that means is that someone clicked on this point in the image, and then the output of this segmentation model was this mask around this person, right? But it's not just the mask. The kind of neat thing with this Segment Anything model is that it also does this kind of hierarchical kind of part to whole stuff for free. So basically you see how it gives you a variety of masks where the masks are kind of ordered with the biggest part down to the smallest part. So when you prompt it with, for example, here, this point where you're clicking on this emu, right? It'll identify the first box it gives you is kind of the largest possible object that could contain that point, which is the full emu. Emu is the name of this bird. Then it'll kind of progressively go down into smaller and smaller pieces. So you see here it goes the full emu, then kind of the top part of the emu, and then the head of the emu. And this is also entirely open vocabulary, right? So there's no notion of specific classes like bird and emu and train and car, right? It's just kind of doing this just through some weird black box magic that it's learned, where it kind of learns to okay, I guess if you're clicking here, the backpack is probably a thing, and then you want the human, and then the zipper within the backpack. So there's no kind of explicit you don't really know what you're going to get, I guess is what I'm trying to say, is that it's open vocabulary and it kind of creates this hierarchy of parts within parts, which is going to be pretty useful for what they do in this paper. Thereby eliminating the need for extensively querying the language field across various scales and the regularization of Dino features. So the across various scales here is, and Dino, this refers to the first Dino paper. So the first Dino paper is also from Facebook or Meta. There's also a Dino V2, which is kind of the more recent version of this work. Most people refer to that, but we can wait for this to reset. The way that Dino works is it's basically a self-supervised vision representation that is trained by doing this kind of weird distillation where they basically crop at different scales. So they crop, for example, this part here kind of randomly, and then they crop within that crop, and then they basically say, okay, whatever the features are within this smaller crop should kind of in some way represent the features in the slightly larger crop. But the problem with this is that you're kind of coming up with these arbitrary crops, right? Like why this particular size crop? Why not a different crop? And what exactly are you cropping? So this having to like kind of arbitrarily pick these random hierarchies of crop sizes to do this part to whole relationship is worse than the kind of part to whole relationship you get for free from the segment anything model. So that's kind of why they're contrasting here what you have to do with Dino versus what you get for free in SAM. Extensive experiments on open vocabulary 3D object localization and semantic segmentation demonstrate that LangSplat significantly outperforms the previous state-of-the-art method LERF by a large margin. LangSplat is extremely efficient and then also better. So this is the most efficient approach and the fastest approach and the best approach for any kind of 3D language semantic-y type segmentation. Listening to it as ASMR while making noodles. All right. I don't quite have like the nice voice though. You know, I need to work on like a particularly like tenor, deep, bassy voice so that, and I need to get a better mic as well. But maybe we work towards that. You know, I try to get one of those like vocal coaches, you know, to improve the sexiness of my voice, and then I also get a better microphone so that we can actually listen to this for auditory purposes. Okay, I highlighted some parts here in the introduction. So obviously the use of this is to interact with and query with 3D worlds using open-ended language, which I think is going to be a big part of kind of VR, AR, spatial computing. If you want to use the Apple terminology, right? You want to be able to, using your headset, you don't want to be like pointing at things. You want to just be able to talk and say, hey, look at that thing over there, and it like segments it out. It already knows what you're talking about. Can you do this X? Can you generate a different thing that's similar to that, right? So interacting in speech is definitely the future, and interacting with speech in 3D, I think, is the future. Feature distillation from off-the-shelf vision language models such as CLIP, so they're going to be basically using these CLIP language features. Learning a CLIP embedding for a 3D point cloud could be ambiguous as CLIP embeddings are aligned with images rather than pixels. So what they're referring to here is that the CLIP model will provide you a feature vector if you give it an image, but you're giving it the full image, right? So the CLIP feature vector is encoding everything, right? So like you can imagine that if you were to feed this entire image into CLIP, that language feature vector would contain kind of notions of the fact that this is a table, the fact that this is a wall, the fact that this is a Rubik's Cube, that there's a Waldo here, right? So there's a lot of different semantic properties of this image that are all kind of competing within that CLIP feature vector. So you want to basically remove all the unnecessary things and only get the CLIP feature vector for the specific part that you're interested in, right? So employing CLIP embeddings from a cropped patch also raises the point ambiguity issue, as the same 3D position can be associated with semantic concepts of varying scales. And this is kind of more what they were talking about here with this Dino, where like here you crop out patches, but like here this patch contains the goat, but it also contains the mountain in the background. So if you were to feed this patch into CLIP, you would get a feature vector that represents both those things, right? The goat and the background and kind of the sunlight, right? There are a lot of different concepts there that would probably pollute that feature vector that you really want, right? Okay. Blah, blah, blah. They shit on the Dino features over and over again. These language-enhanced Gaussians are supervised using CLIP embeddings extracted from image patches captured from multiple training views, ensuring multi-view consistency. So Gaussians and any other kind of 3D representation, generally the way they're constructed is from these multi-view images. So you basically have many different two-dimensional images from multiple views of the scene, right? So here you have the bear talking to the stuffed goat on the table, and to begin this process, you just need a bunch of pictures from multiple views, right? Okay. Directly storing the high-dimensional language embeddings for each 3D Gaussian model is memory inefficient, right? So each feature vector from CLIP is like 512 numbers, and that's just way too many numbers if you have a million Gaussian splats. So you kind of want to reduce that down to a smaller amount of numbers, and the way that they're going to do that is by training a scene-wise language autoencoder. And the part of this that sucks is that it's a scene-wise language autoencoder. So anytime you have something like that that is scene specific, that means that for every single scene, you're going to have to basically train a new one of these language autoencoders. So that's kind of the kind of letdown with this paper, is that it's basically scene specific, and the purpose of this little autoencoder is to map these clip embeddings into a low-dimensional latent space, basically just to reduce the total amount of numbers that you have to basically assign for each of those Gaussians. But one of the other papers that we're going to look at today is this one here, this Compact 3D, which is compressing Gaussian splat radiance fields with vector quantization. And I think that the technique that they use in this paper to compress these Gaussian splats would actually work very well for this exact problem, and they would remove this need to train a scene-wise language autoencoder. So we'll look into that a little bit further in the future. But each language Gaussian only contains a low-dimensional latent language feature, and the final language embeddings are obtained with decoding the rendered features, which is now doubly bad. So now not only do you have a scene-wise, so scene-specific autoencoder to kind of compress these language features, but now if you actually want to get the language feature with an associated Gaussian splat, you have to run it through this little, the decoder, so extra inference as well, which sucks. They're going to really kind of lean on this semantic hierarchy defined by the segment anything model, right, which is the fact that the segment anything model gives you this kind of weird hierarchy that kind of grows in the parts to whole kind of nature of it. What else? We're going to scroll through the related work here section. They mention, of course, Gaussian splats. They also mention the segment anything model, and they also talk a little bit about previous techniques such as LERF within the creation of 3D language fields. So now we're going to go into the proposed approach, which is effectively the method section, and here's where we're going to get really mathy. This stream is going to get pretty intense pretty fast, so if you guys want me to pull out, just let me know. We're going to start with an input image I. So here we have a standard input image, three-dimensional, or 3 channels, red, green, and blue, and then some height and width. You have a set of these images, and the calibrated here refers to the fact that you know kind of where these images are. So Gaussian splats are very sensitive to initialization, so you kind of need to know the exact kind of camera information for these images. So you basically need to know where these images were taken from. So the camera extrinsic matrix or the camera position in the global coordinate frame is kind of what you need, and that's what they mean here by calibrated images. So you have some set T of these images that are kind of multiple views of some scene. The goal is to then train a 3D language field psi, right? And you're going to be able to query that 3D language field with any point in space and then get some vector back, and that vector is going to be the image or the feature vector of the kind of text language semantic-y stuff. They're going to be using the clip image encoder, so they're using the pre-trained and frozen clip image encoder. They're using the pre-trained and frozen segment anything model. Supervise, leveraging the well-aligned text-image latent space, facilitating open vocabulary queries. Computing the V only obtains image level features, whereas we need a pixel-aligned language embedding, right? So they don't want the feature vector for the entire image. They want the feature vector for just the specific part of the image that they want. And obviously, you guys are kind of seeing where this is all going. They're going to be using the segment anything model to basically crop out very specific parts and then feed only those very specific parts into clip to get these clip feature vectors of dimension D, right? So here the LT is basically you have one clip feature vector D of depth D for every single pixel in HW. Blah, blah, blah. Okay, I think this is maybe we do a little bit here. There's a high demand for efficient open vocabulary querying in practical applications, especially in fields such as intelligent robotics, right? So this is another huge, it's not just VR, AR, like we're talking about robots, right? So imagine a robot in your house that's operating, and it needs to be able to basically segment things out in the 3D world and then understand where those things are. So like this type of like language-based querying is going to be very important in robotics when robotics is being done with language models, which is kind of what we're seeing, right? So right now, most robots are not kind of, the internal kind of state machine inside these robots is usually kind of more explicit, more heuristic. But I think as we move into the future, it seems like kind of the robots that we're going to have are going to be more operating in almost language space, right? Which is, at least in some of the stuff I was doing in robotics, that's the space that I was using to do all the kind of planning and intelligence, right? You're basically, the robot is talking to itself in English and coming up with plans in English, right? So if everything is in not just English, but text, right, then being able to say, hey, I need to pick up something up from this table, I need to pick up the spoon, and then now you can say, okay, well, where is the spoon? You should be able to now query your scene and your environment for something called the spoon, right? The way that would be done classically is then, okay, now you have an object detector, you're going to detect the bounding box for the spoon, and then you're going to use that bounding box to segment out a specific part of your 3D representation of the space. But I think all of that is going to get squashed and simplified, and we're basically going to be in a world where I think the world representations inside these robots are going to be Gaussian splats. I think it's a matter of time. You know, I'm a believer in Gaussian splats, but I think all the current simulation frameworks that exist for robots, which are being used inside these robots to do a lot of the path planning and a lot of the kind of stuff like that, like I think those are going to be replaced by Gaussian splat based rather than kind of what we have now, which is texture and meshes and voxels and stuff like that. Okay. Hierarchical semantics with SAM. Obviously, they're going to be using the segment anything model to basically get what they call the whole, the part, and the subpart. So the whole, the part, and the subpart are basically the three levels here. This is the whole, the part, and then the subpart. And there's no formal definition there, right? You're kind of just whatever SAM decides is the whole, the part, and the subpart, that's going to be whatever SAM decides. So that fuzziness would normally not be great, but here they're kind of leverage the fact that fuzziness allows them to do it all in a kind of an open vocabulary. In 2025, this will just convert into a Yerba Mate ASMR channel. Yeah, pretty much. It won't even be me. It'll just be like an AI version of me that just sits here and reads things while casually sipping Yerba Mate. Okay, so the way that they're going to prompt the segment anything model is with a grid of 32 by 32 points. So you can prompt the segment anything model with points, right? So for example, the way that they get these example images is basically you just prompt it with a grid of points. So just imagine a bunch of points there, and then the segment anything model runs for each of those points. That's actually the way that they prompt in these examples. So that makes me think that they just literally took the example SAM and used that. So when you prompt for each of these 32 by 32 points, you're going to basically get masks. Masks are binary images where everything is 0 except for the stuff that you're interested in. So when you look at a mask, you kind of see this like kind of like outline, but really every single one of these colors is basically a binary image where everything is 0 except for what is this, and then this would be 1, right? So it's basically masks are these binary images. So you have masks for the subpart, the part, and the whole, right? 3 hierarchy levels for every single one of these 32 by 32 points. They remove redundant masks because sometimes when you're just using this grid of points, you'll have 2 points that kind of land on the same thing. So here, for example, this dog, you would hit multiple times with this grid of points, and so you would have multiple masks that are duplicate because they're just the masks of the same exact dog. So you get rid of those duplicate masks. And 3 segmentation maps, whatever, is the same thing, right? Segmentation maps is kind of, think of it like a mask, but then rather than 0 for nothing and then 1 for the object that you want, in a segmentation map you might have more than just 0, 1. It might be the index might actually be the name of the class, right? So maybe 0 for background, 1 for dog, 2 for something, whatever. But these segmentation maps precisely delineate the boundaries of the objects at their hierarchical levels, right? So 0, 1, I guess 1, 2, 3, 0, 1, 2 for the hierarchy level. With the obtained segmentation maps, we proceed to extract clip features for each segmented region. So here you can see they're taking their segmentation maps, right? This is the Hamard product, which basically, because this is just a bunch of zeros and then there's a bunch of ones, this is element-wise. So basically, you're just extracting out the parts of the image that are not masked out. So this is just basically you're masking out everything that isn't part of that image. And then you're feeding it into V, which is the clip image encoder here. Clip image encoder V, and that'll give you a little feature vector that represents basically the semantic concept in that mask. So here's kind of an image to show you what's going on. Here you have your multi-view images, your set of images that are all nicely calibrated. You know where exactly they are. You're feeding them into SAM. The segment anything model is giving you these binary masks for different levels of hierarchy. So you have the whole, the part, and the subpart. You have basically the full sheep, the head of the sheep, and then I guess just the inside of the ear of the sheep. Is that what that is? And then you feed each of these into clip. You're going to get basically little feature vectors for each of those. And this is the kind of part where they basically compress it. So normally you could basically then just take the feature vectors that come out here and then just assign those to each of the Gaussians in the Gaussian splat. But these little purple points are 512 dimensional, which means they're quite heavy. So they're going to try to compress them down using this encoder decoder. So the encoder will basically compress it down to, I think it's 3 numbers. So it's just a 3-dimensional little feature vector now. And then that just reduces the memory overhead, but the problem is now if you want to, for example, query, you're going to say, oh, I want this point here, then you're going to have to feed that point through the decoder and then back through here to get the actual language. So unfortunately, a little bit of extra steps there. 3D language or 3D Gaussian splatting for language fields. A set of 2D images, L. Okay, it's the same as we had before. We can learn a 3D language scene by modeling the relations between 3D points and 2D pixels. 3D Gaussian splatting, here's a little summary of Gaussian splats, in case you didn't know. But Gaussian splats are basically a collection or a set of anisotropic 3D Gaussians, with each Gaussian characterized by a mean and a covariance matrix. So the mean is basically just the position in 3D space in R3, right? So 3 numbers that represent the position in 3D space of this little Gaussian little splat. You have a covariance matrix, which is basically the spread. You can think of it that way, like how is it like oblong and shaped? Usually this is broken down into the scale and then the rotation. So you'll see in these other papers, for example, this one here, they also have a definition of Gaussian splats, right? Every single one of these papers has a part where they explain what Gaussian splats are, but some of them are better than the others. This one is the more explicit one, and in this one, right, they break down the covariance matrix into this rotation component and this scale component, where the rotation component, here it's a rotation matrix, but rotation matrices are 9 numbers, right? Because it's a 3x3 matrix, versus a quaternion is 4 numbers, right? So you don't want to store 9 numbers for every Gaussian, you want to store 4 numbers for every Gaussian, so that's why you parameterize the rotation as a quaternion. Okay, so here you have just basically the equation for a Gaussian here. You have the mean, and you have the covariance. The way that Gaussians work is they do this tile-based rasterizing. Basically, they cut the image into these tiles, right? N is the specific tile. And then for each of the tiles, they will sort the Gaussians, basically front to back. So basically the Gaussians that are closer to the image versus the Gaussians that are in the back. And then they'll render them. And then they'll basically do this right here, where they're basically multiplying the color, which is CI, by the opacity, which is alpha, right? So here's another typo here, PXIL. But you can basically think of it like each of these Gaussians is a little bit see-through, right? That's what the opacity means. And then because you can sort them based on the camera view, you can kind of render them and add up the colors such that the ones that are closer to the camera kind of have preference. And then as you get further and further back, the color gets harder and harder to see through the other Gaussians. And then at some point, you can't actually see the Gaussians behind a certain point. And this tile-based kind of sorting and rendering is really, really fast on GPUs. And that's kind of the secret magic behind 3D Gaussians, right? Is that this particular type of rendering is fast. And that's really why NeRFs got beat by 3D Gaussians, is because NeRFs, the rendering is this kind of ray marching that you have to basically, every single ray, which is basically every single pixel, is a inference through a multi-layer perceptron. So even though a NeRF is much smaller in terms of like the total amount of memory and the size, because all you're storing is this little multi-layer perceptron, right? The rendering is so slow that the Gaussians won out. And the Gaussians are also more explicit, which means that it takes more memory to store a Gaussian, because you have to store literally millions of points with little centers and stuff like that. But I think that the explicit nature of Gaussians is actually a benefit, because it means that you can do segmentation, you can cut parts out, you can put things in, you can combine them more easily. So I think the explicit nature of Gaussians means they're more composable, which I think is a property that is very important for robotic simulations and 3D design and stuff like that. There's so many properties, there's so many workflows in the 3D world where you want to be able to separate parts or combine things, and I feel like the explicit nature of Gaussians makes them way better for that than what NeRFs were. Okay. But you have your little Gaussians, each of them has these properties, right? And now in this paper, we're adding these extra properties. We're adding basically 3 new language embeddings, FS, FP, and FW. So every single Gaussian splat is going to have basically 3 clip feature vectors corresponding to the clip features that you get when you feed the 3 hierarchical pieces of the part, or the whole part and subpart, into clip, right? So you're going to end up with 3 vectors there. But those 3 vectors are quite big, right? They're 512 dimensional clip features. So you want to compress them down, right? So how are we going to compress them down? We're basically going to use this scene-specific language autoencoder, which is going to autoencode. This autoencoder maps clip embeddings into a scene into a lower dimensional latent space, reducing memory requirements. Not great, but got to do what you got to do. The language field is scene specific. This is the part that sucks, meaning we can leverage scene priors to compress clip features. That's not a benefit, that's a negative. We will obtain hundreds of masks segmented by SAM, which is significantly smaller than the number of images used in clip training. Therefore, all the segmented regions in the scene are sparsely distributed in the clip latent space. Okay, so what they're saying, they're kind of trying to justify why they can do this, right? So one way to argue against what they're doing here is you're saying, hey, well, even though this is 512 numbers that describe this object, right? If you try to compress that, you're going to lose information. So you're going to lose that richness of the clip feature space. But their argument for that is that, okay, but we're only constrained to one scene, so therefore these particular points are actually going to be quite sparse, which means that you have the opportunity to compress them and still retain a little bit of their kind of like meaningfulness. Kinda, maybe, I don't know, like I see where they're going with that, but then I would say that if the more complicated and semantically busy a scene is, right, the more that argument is going to kind of fade apart. But largely, the reason they're doing this is not that. The reason they're doing that is just to save on memory, right? An encoder maps the d-dimensional clip features, right, that big D, which is the 512, to the small d, which is, I think, 3. So much smaller, much less amount of numbers. The autoencoder is trained with a reconstruction objective on the clip embeddings. So basically, they're trying to reconstruct those clip embeddings, those 512 dimensional vectors. So the loss here to ensure, because this is pre-trained and frozen, right? The SAM is pre-trained and frozen. Clip is pre-trained and frozen. But this encoder and decoder you train from scratch for every single scene. So the loss that you use to train this encoder and this decoder is basically you're just reconstructing. So you're taking this 512 dimensional vector, you're crunching it down to 3 numbers, and then your decoder's taking those 3 numbers and trying to crunch it back up, or uncrunch it back to 512, and you basically do an L1 loss on every single one of those. So here's your language vector. You're encoding it, then you're decoding it, and then you have this auto-encoding reconstruction loss there, which is just L1 and then cosine distance. Okay. What else? We use the trained scene-specific decoder to recover the clip image embeddings. This is the part that kind of sucks as well. So not only are you kind of have this scene-specific part, but now if you actually want to query the scene, you're just going to get back this little three-dimensional d=3 little vector. So you can't use that. That like doesn't really mean shit. So you're going to have to feed it into your decoder to actually get the clip vector, which then you can actually get the text, which is what you ultimately want. Okay. Powerful and efficient solution not only preserves the rendering efficiency, but mitigates the catastrophic memory explosion associated with explicit modeling. Kinda, or you could just wait for these things to just get bigger and computers to get faster, and then you're completely fine. Or you can do the technique that we're going to look at in the compression paper. Open vocabulary querying. Okay, so now we have a Gaussian splat that has little language features for every single splat. So every single one of these splats has 3 numbers that are basically represent the language features, and you can always feed them through a decoder and get the full clip features if you want to. But how are you going to now do this open vocabulary querying? So you're going to have some kind of text query, which is the question I'm asking. So I'm saying, where is the bear? Or give me the bear, and it's going to have to segment out the bear. So how is it going to do that? Well, it's going to take this text query, and then it's going to calculate this relevancy score. And this relevancy score is basically going to be the dot product between the query and then the language embedding. So basically it's going to look at every single Gaussian splat, and it's going to say how similar is this query to the embedding, but then also they have to kind of like regularize this or normalize this. So they're basically also looking at how similar that image is, or that feature vector for the image, this phi image, to what they call a canon phase. And the canonical phrase, I think this is also a typo, this should be phrase. The canonical phrase is basically the clip image embedding for object, thing, stuff, and texture. So it seems like basically the clip embeddings that you get from each of these objects, like not only do they encode, like for example, elephant and blue, but they're also encoding object, thing, right? Because it's like, this is a thing, it's an object, right? So like the clip semantic representation includes that kind of notion of this is an object, this is a thing. So they're kind of trying to like get rid of that objectiness in that feature vector. So they really just want the best matching language feature vector to the original text query that you're asking. And then so that's how you get the best point, right? If you're doing this open vocabulary querying, and then if you want to do the full segmentation like they do here, then you basically filter out points with lower relevancy scores than a chosen threshold, and you have some specific list of objects like this. So that's how they get this full set here. And I think that's basically it. If we look at the I haven't read much on splats, but it makes it sound too much like diffusion. It sounds like 60 pose detection. So every single one of these splats has a specific pose, right? It has some center. It has some mu, which is the center, right? This part here. And then it has this covariance, which is effectively, you can think of it kind of like the rotation and the scale. But there is no notion of the whole object, right? So this object, this blue elephant here, is not a single splat. It's basically like hundreds of splats, probably thousands of splats, because each scene is like 1 million splats. So there's probably thousands of little 3D splats that represent this elephant, but there's no notion of the orientation or pose or 60 pose of this elephant, right? So that's actually something that makes sense, Jay, that isn't here, right? So in a lot of 60 pose detection, like historically, normally you would get a 6-dimensional pose that represents this entire elephant vector, but here there's no notion of that. You get like an objectness kind of. You could basically say, okay, well, all the splats that are associated with this elephant, I can segment them, and now I can have basically the elephant itself as a little Gaussian splat, but it's composed of hundreds of splats, so there's no 60 pose there, you know? Yeah. that could be a paper. You could definitely do that as a paper. 60 pose from splats. You probably do some kind of like ICP, the iterative closest point kind of stuff. Let me see. There's a nice GIF for not Insane Clown Posse. Computer vision. Yeah, iterative closest point. This is kind of matching. You could probably do something like this for Gaussian splats. Wow, there's like a GIF though that I want to see. This GIF. I think this is the GIF. What the fuck is this crap? Make a GIF. Yeah, so this is iterative closest point, which is how you can match together 2 point clouds. And Gaussian splats are kind of similar enough to point clouds that you could use basically that same algorithm to get a 60 pose if you have already existing splat for this little elephant. Okay, so they try this out on the LERF dataset, which comes from the iPhone app Polycam. They also try this on the 3D OVS dataset, which is some open vocabulary 3D semantic segmentation dataset. They use the OpenClip VIT-B16, so VIT big with 16 patches. So this is a vision transformer. There's a lot of different types of clip. So whenever people say clip, there's actually like 12 types, or like probably more than that at this point, types of clip. There's big clips, there's small clips. So here they're using this particular clip, and then the segment anything model also comes in various sizes, I think, and people have even distilled, so there's very small segment anything models, but here they're using the VITH version of the segment anything model, which I think is huge, so slightly bigger. Each scene comprises around 2,500,000 points, so each scene like this is 2 million Gaussian splats. There's 2 million points here, right? Which now makes the whole situation more obvious, right? Of like, imagine if for each of these 2 million points, you only have to store 3 numbers. That's way better than imagine if for every single one of those 2 million points, you had to store 512 numbers, right? Like that would just explode the amount of compute and memory you need. So that's really the whole like autoencoder to reduce it down to 3. Like the only reason they're fucking doing that is because you just can't fit 2 million times 512 on like a reasonable computer. But I think you just wait 2 years and you can do it. So that's that. Autoencoder is basically just a bunch of multi-layer. It's just multi-layer perceptrons. I don't think you need the S here, right? Like the multi-layer perceptron already is plural, so I don't know why MLPs. It should just be by an MLP. I guess maybe you have the encoder decoder, so MLPs refers to MLP for the encoder, MLP for the decoder, but the plurality on there, MLP with an S, that kind of felt weird to me. 25 minutes on an NVIDIA RTX 3090. So the 25 minutes is basically coming from the fact that they have to train this autoencoder per scene, right? So not only are they making this splat, but they also are training this little autoencoder here, which takes time. So that's the only part that sucks with this, but I think it'll eventually be solved, right? People will extend this, but looking pretty good, you know? Look at this. Compared to LERF, which is the NERF-based one, the language NERF, it really does seem significantly better. So Gaussian splats, absolutely killing it right now. You know, it's like basically take any NERF paper, implement it in Gaussian splats instead, and you're going to get state of the art. So there's like all this low-hanging fruit right now in computer vision research where you can take all the cool shit that people did with NERFs and then just basically do it in Gaussian splats, and it's probably going to work better, which means you're going to be able to put state of the art on your paper. Right, like they didn't even use a different data set. They used literally the same fucking data set so that they can directly compare to LERF. This paper was literally made to destroy LERF. It was created with only one purpose. Gaussian splats seem exciting. They are turbo exciting. I wonder why they need 2 million points. So much potential to compress this from Spirobel. So actually, Spirobel, that's the perfect transition to this paper. So this next paper that we're going to look at is a little bit older. This is from 30th November 2023, and this is called Compact 3D, Compressing Gaussian Splat Radiance Field Models with Vector Quantization. So we have Gaussian splat, and you're compressing them, right? So you're kind of reducing the total amount of size, right? And the size is coming from the fact that you have 2.5 million points, right? You have 2.5 million points, and for each of those points, you're storing all this information: the center of the Gaussian, the rotation of the quaternion for the Gaussian. You're storing the color, the opacity. Now you're storing this language information for each of those, right? So that's a whole lot of shit. How are we going to reduce the total amount of memory? Well, the way we can do it is with vector quantization. So vector quantization, you guys probably already know what this is. If you've ever heard of a VQ-VAE, or the VQ there stands for vector quantization, right? So what vector quantization is basically this idea where you create a code book and then you store basically references to the code book, which is cheaper than storing all the information explicitly. So I don't know if I described that well, but I think once we go over this paper, it should be pretty clear for you. The idea here is actually quite simple. It comes with a drawback and the much larger storage demand compared to NeRF methods. So here they're talking about how NeRFs, obviously all you need to store is this little multi-layer perceptron, so they're really, really small, but the problem with the NeRFs is the rendering, right? We notice that many Gaussians share similar parameters, and that's kind of the boom. That's the insight. So we introduce a vector quantization method based on k-means algorithm to quantize the Gaussian parameters. K-means is basically you're clustering. It's a type of clustering algorithm where you sort a bunch of data into k clusters. I think there's let me see if I can k-means clustering. I bet you there's a cool GIF for this that kind of makes it immediately apparent. I can't really find a GIF, but like this is basically k-means, right? You have like some original data, and then you're basically creating these cluster centers. So you see that black point there, that's the cluster, and k-means is this kind of like iterative algorithm where you initialize these cluster centers, and then you kind of like have them move and shift, and then the k, I think it's like it might be the k nearest points or the k total cluster centers. I don't know exactly what the k refers to, but over time you eventually get these 3 center points, which represent roughly the different clusters of your data, right? And what they're going to be doing, oh my god, I keep going to the wrong paper, but they're going to use the k-mean algorithm to basically group up and cluster the Gaussian parameters and then vector quantize based on that. So you can think of it this way, right? So if we go back to here, right, think about this, right? We have our blue elephant. That blue elephant, if this entire scene is 2 million points, that blue elephant might be 1,000 points, right? But every single one of those 1,000 points here that represent this blue elephant, those 1,000 little Gaussians, they probably have the same exact color, right? So there's 1,000 of your Gaussian points are literally 3 numbers in there, which is the RGB, the color. They're just storing basically the same exact color of blue over and over again, right? So like you're spending all this memory to store 2.5 million Gaussians, and each Gaussian has these properties, and it turns out that actually a bunch of those properties are actually the same fucking number, so you're just storing that blue color over and over and over and over and over 1,000 times, right? So that's kind of what they're coming to here, is they're saying, hey, what if we just cluster these Gaussian parameters and then store a small code book which contains basically the centers, right? The centers of these means, and then that's what we store. So we only store the color blue once, and then we basically store the index that says, okay, the color of this Gaussian is index number 0 in my code book that has the colors, right? And that's effectively what this paper is. Along with the index of the code, moreover, we compress the indices further by sorting them and using a method similar to run length encoding. This is like extra sauce. Like I thought this was a little bit overkill, but just to show you guys what run length encoding is. Run length encoding is a pretty ancient technique. You can see how old it is based on the formatting of this text, but it's a way of basically compressing information. So you can see here in the original data stream, you have this stream of numbers, and here you have a repeated 3 zeros in a row, right? So you could store each of these 3 zeros, or you could store 2 things instead by saying, okay, here's a 0, and then there's 3 of them, right? Or here's 5 zeros, and I'm just going to store 0, 5. So it's basically you're storing a a larger stream of numbers with a smaller stream of numbers by basically leveraging the fact that you can remove these duplicates. And the place that I've seen this before is masks. So when you're storing, for example, binary image masks, right? Run length encoding is actually very popular there because a binary image masks is basically a bunch of 0000000111100000000, right? It's just basically this binary image. So that is almost tailor-made for run length encoding, right? But it's also very annoying because then you have to basically decode it if you want to use the mask. So it kind of has a similar kind of issue to that paper, to the earlier paper, where you're basically, as soon as you encode something, now anytime you want to use it, you have to decode it. So I feel like they were just trying to really juice the factor here of 20x smaller, but I feel like if they would have gotten rid of this run length encoding, it would have just been a little bit nicer. I also feel like it's a little bit overkill to compress the indices to the code book with run length encoding like that. Okay, that's just unnecessary, just showing off, trying to flare. November 23rd, outdated, toss it. We do expensive experiments as well as a new benchmark. We show that simple yet effective method can reduce the storage cost for the original 3D Gaussian splats by a factor of almost 20x. Okay, and let's keep going. One of the main drawbacks compared to NeRFs is that Gaussian splatting needs at least an order of magnitude more parameters. Main intuition is that several Gaussians may be able to share some of their parameters. Hence, we simply vector quantize parameters and store the codebook along with the index for each Gaussian. We use the quantized model at the forward pass, updating the non-quantized model at the backward pass. This is, they actually, the codebook is not done at the very end, so it's not like they have a final Gaussian and then they basically k-means and then write a codebook for that. They actually, the Gaussian and the parameters are being learned at the same time, right? At learning time. So the choice of what is in that codebook is happening during training. We update the centroids of the k-means at every iteration, but update the assignments less frequently. The assignments is basically when you're doing this k-means, right? It's an iterative algorithm, and you're going to be updating the centers, but then occasionally you have to update the assignment. So you see how this point here is green? Every now and then you would update the assignment, which means you might actually say, okay, well, this point that used to be green, now it's closer to this red one, so we're going to relabel it as red, right? So that's what assignment reordering is. And then they're storing the indices to that codebook with the run length encoding, which I think is a little bit overkill. So let's look at a picture of this to kind of really cement this in our head. This is figure 2, overview of CompGS, which is the compressing Gaussian splats. We compress using vector quantization of the parameters of the Gaussians. The quantization is performed along with the training of the Gaussian parameters. So the choice of what's in these codebooks is being done during the training, which is actually more similar to a VQVAE. Like, this paper just reeks of VQVAE to me. Even though it's... Actually, there's nothing similar to this, never mind. But considering each Gaussian as a vector, we perform k-means clustering to represent the n Gaussian models with k-cluster centers, or codes, right? The code book is a list of these, basically... That blue color that's coming up 10 billion times, that's what you're going to store inside this code book, right? So you're storing, but it's not just the colors, right? You're storing all kinds of shit. You're storing scale, rotation, color. So if there's a bunch of Gaussians that have the same rotation, rather than storing that rotation, that rotation quaternion, which is going to be 4 numbers, rather than storing that same rotation 20 times or 10,000 times, you basically store it once in this code book, and then what the Gaussians have is each little Gaussian splat just basically has a index that says, my rotation is index number 2 in the codebook, and you go to index number 2, and index number 2 is those 4 quaternions, or the 4 numbers that represent that quaternion. Each Gaussian is replaced by its corresponding code. The gradients with respect to the centers are copied to all the elements in the corresponding cluster, and the non-quantized version of the parameters are updated. Only the codebook and the code assignments for each Gaussian are stored and used for inference. This is where you're going to get obviously the memory improvement. You can see that before you have 200 megabytes to store all these little Gaussians and all their parameters, and then if you use this codebook, you get it down to basically 10 megabytes. And that's basically it. You have a little reconstruction loss there just to make sure that you're not kind of losing too much information by using this kind of codebook. but pretty cool, 59 parameters per Gaussian. The storage size of a trained model is an order of magnitude larger than most NeRF approaches. So here there's lots of different 3D Gaussian splats, right? And pretty much every single Gaussian splat paper has a slightly different parameters for each Gaussian splat, right? The simplest version of it would be the center and then the color. So 6 numbers, right? RGB and then XYZ. But you can have a lot of parameters, right? It gets more and more complicated. We're going to look at a paper at the very end here that has a huge amount of parameters per Gaussian. But here in a typical scene, they're saying we have 59 parameters per Gaussian, right? And actually, if you think about this, right, now imagine having an extra 9 parameters corresponding to the three-dimensional language features, or even worse than that, to each of those 59, adding another 512. But that's where I think this Gaussian compression could actually work very well with the language stuff, right? Because in the language stuff, they have to do all this crap here because storing this 512-dimensional vector takes up way too much memory. So instead of that, what if they used this and they basically had, what if they used the technique here, and then as part of their code book, they basically had the language feature. So now all you have to store is the index, because I bet you that a lot of the stuff in the image is probably the same language feature. So there's a lot of Gaussians here that are representing maybe this wheel, and all of those could basically point to the same language feature vector inside the code book. So I think there's a synergy between these papers. Okay, that's pretty much mostly this paper. Their codebook size is 512 for the color, 416 for the covariance parameters. So there's basically like 5K indices or 5K entries inside this codebook, and then you have whatever 2 million Gaussian points, which are basically the parameters are no longer fully stored. They're basically stored in that codebook, and you're storing the index to them. They use tanks and temples, deep blending, MIP NeRF. This is their data sets that they're using for evaluation here. What do we got? We got different techniques here. Planoxels. Planoxels is kind of almost like the proto Gaussian splats. These are like older, but like I think they're like the historical legacy, not historical, what am I trying to say? Like they're a kind of more explicit type of 3D representation that kind of popped up for a brief time. I feel like a long time ago, but now looking back in hindsight, knowing that Gaussian splats are the future, it's like we should have seen planoxels as kind of a little bit better, but planoxels got overwhelmed by NeRFs, and then now we're back to the more explicit Gaussian splats. So here you have a NeRF, you have the instant neural graphic primitive, I think this is also a NeRF, and then the 3DGS, and then the compressed one. So here's the memory. You got 54 megabytes versus 607 megabytes, so that's the compression you get on the NeRF side, or from just a normal Gaussian splat to this compressed Gaussian splat. If you compare to something like a NeRF, obviously the NeRF is way tiny, right? Because it's all you're storing is basically just that little multi-layer perceptron. But the problem is this: look at the FPS for these NeRFs, 0.09. That's absolute dog shit compared to look at these Gaussian splats, 142 frames per second. So this is kind of the trade-off, right? It's like more explicit, more memory, but faster rendering. Versus NeRFs are really shitty rendering speed, but very tiny amount of memory. And then here planoxels, which I think it's like the proto NeRF, right? Like in your head, think about like one of those like proto mammals, like one of those like the short-faced bear compared to like today's like grizzly bear. Like planoxels are like the short-faced bear. So not very good. Kind of shit on both metrics. It's like just barely faster than NeRFs, and then like way bigger than the Gaussian splat. So that's that. The results, here you go. Obviously, in a compression paper, you're going to get shittier results, right? Like you're gonna lose some amount of information because rather than explicitly storing every single color for every single splat, now you're basically storing a smaller amount of colors and they're referencing that color. So like you're gonna get a little bit of just loss of quality. It's not going to be quite as good. For something like this, it'll be better. So I don't know what Dr. Johnson is, but it's like some kind of picture, and here you have a white wall. So obviously there's a lot there's a lot more similar colors here, which means that the compression is going to work better. I think the more kind of visually similar the scene is, the more you can expect this compression to not reduce the quality, right? So these seem a little bit cherry-picked, right? Like all of these, it's like you have this big giant blue thing, which is all the same blue color, all the same background here. Everything in the road is probably the same color. The sky is the same color, so. And then they do this on an RTX 6000 GPU. Damn, you guys are popping off here. Small systems, when you guys compact neural graphic primitives with learned hash encodings. Okay. Or hash probing. Supersplat has a blog post about compression too. Yeah, I think this compression could work, but the problem is now you have this code book, right? So it's like you run into these same problems, right? So like the same thing here, right? Where by using this autoencoder, they reduce the total amount of numbers that they need to store. But now, anytime you want to do anything, you basically have to feed this little three-dimensional vector that you created into this decoder. So if you're thinking about you have this on a VR headset, right? Now you have to store this little decoder model on the VR headset, which is fucking annoying, right? Same thing here, right? So it's like you saved all this memory, but now you have to store this code book, right? And what if the code book is like kind of weird in some way, you know what I'm saying? Like, and now you have to store this code book in a potentially different place. It's like the more models you need to load to have a specific workflow and a pipeline work, the more annoying it is. It's really convenient if everything is just one big model and that's the only thing you need to load, right? Having to load like 4 or 5 different little sub models like this, and then you have a little code book and you load the each of the splats in a separate little thing. It's like, I don't know, I feel like that extra complexity, maybe you lose something there, but obviously if you're getting 20x compression, then it's probably worth it. Okay. So those were the easy papers, guys. So those 2 papers we read, they might have seemed a little bit mathy, but this one is the king, right? And we saved this one for last. This is called Space-Time Gaussian Feature Splatting for Real-Time Dynamic View Synthesis. 28th December 2023, and this is a paper that tries to basically add dynamic or time to these Gaussian splats, right? Like up until now, everything we've looked at, all of these splats, they're frozen in time, right? They're just like this frozen moment in time. Nothing is moving, everything is stationary, and that's basically it. You can get new novel views, but it's basically like a picture, right? It's like a 3D picture, but that's not the Holy Grail, right? What the Holy Grail is videos. We want 3D videos. And we've read some of these papers before, but every single time people try to make these dynamic Gaussians, it's always this absolute tangle of fucking math because it's just fucking hard. You know, it's really hard to add this time dimension into these splats. So maybe let's look at the videos that they released with this, because I think these are pretty cool. So here they have a 3D Gaussian splat video, right? So basically the Gaussian splats are changing over time. Here they're basically showing you a couple different views to show you kind of how the view changes over time, or to show you the exact center of the Gaussian splats, but you can apparently do real-time 8K. So I don't know, this is like, to me, this is the future, right? Like, we're all going to be living in 3D worlds like this. We're currently in this weird paradigm where we have these cell phones that are 2D, so everything is 2D, right? Like all your social media feeds are 2D. But I think that's going to end very quickly. I think that once we have the Apple the Apple headsets, the Quest headsets, I think that we're very quickly going to start getting into 3D, and then everything is going to start being 3D. So all the videos you take are going to be 3D videos. Everything is going to be 3D. So I can't wait. You know, I can't wait to be like to be able to like move anywhere within this 3D video. But okay, how are we going to do that? Because these Gaussian splats, you're going to need to add some kind of dynamic properties to each of these little splats, right? So the way that they're going to do this is by adding what they call temporal opacity and parametric motion and rotation. All right. So really, there's two main parts. They basically want this enable. Actually, let me just read the abstract, and then I think it'll be easier to do that. Simultaneously achieving high-resolution results, real-time rendering, and compact storage is a formidable task. We propose space-time Gaussian feature planning, splatting as a novel dynamic scene representation composed of three pivotal components. We have the temporal opacity, the parametric motion and rotation, and then they also try a slightly different approach for the colors using basically what ends up being like a mini NeRF instead of the spherical harmonics, but we'll go into that later. They leverage the coarse and depth, blah, 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 state-of-the-art rendering quality and speed, so another state-of-the-art paper here. And it renders at 60 frames per second on an NVIDIA RTX 4090, which is a consumer GPU. Okay, so Spacetime Gaussian extends 3D Gaussians to the 4D spacetime domain, right? So 4D spacetime, the 3 dimensions of space, and then the 1 dimension of time. Instead of storing, we'll go to that later because I think that it's a little bit confusing to look at it now. So here in the preliminary section, obviously they're going to have their own little definition of Gaussian splats. Every single one of these papers has a little definition of Gaussian splats. So this is something I like to do. Like normally whenever you read papers like this, I'll go to this section like that and they'll each give you their own little explanation of Gaussian splats. So you can read all 3 of those and then all of them are slightly different, and then it's almost like reading 3 different paragraphs that explain the same thing is a much better way of understanding the thing than just reading one paragraph that explains the thing. So if you ever want to learn something like that, right, you can basically find a bunch of papers that are all on that topic, and then in the kind of preliminary or background section, they will explain that kind of core concept, and then you will get basically whatever 8 explanations of that core concept. So very efficient way to learn if you want to kind of do a kind of almost like a mixture of experts for learning. Okay, so basically you have your Gaussian splats. Each little Gaussian splat has some position. In the other one, they called it the mean, but it's basically the 3-dimensional center. You have your opacity, which is the see-through. You have your covariance, which is effectively basically the like kind of rotation and kind of spread and squash like that. But then they also have what are these spherical harmonic coefficients. So spherical harmonic coefficients are basically numbers that represent the coefficients of spherical harmonic equations. So spherical harmonics is basically it's harmonics. Think about like constructive, destructive interference of waves. Think about like that kind of thing. But basically, it's a way of kind of describing positions on a sphere. It's a way of kind of encoding. It's kind of like a position encoding for information, for sphere information. And these spherical harmonics are very popular for storing view-dependent effects, right? So what do I mean by view-dependent effects? So when you have a little Gaussian splat for something reflective, let's say this cup, right? The Gaussian splat right here is black, right? Because this cup is black. But the little splat, whenever you look at that point on this cup, there's a particular view angle where suddenly the color of that goes from being black to suddenly being white because it's reflecting the light, right? So there's these view-dependent effects that are changing the color, right? So this view-related information. So how are you going to store that view-related information that changes depending on where you're looking at it? Well, you can use this, right? You can basically use these coefficients to say, okay, well, you're looking at it from this angle, which is some combination of these spherical harmonics, the color should change by this much, right? There should be, usually it's for color. But that's the way that people normally store these kind of view-dependent effects. But in this paper, they do a little trick where basically rather than storing it in the spherical harmonic coefficients, they instead store it in a multi-layer perceptron, which is effectively a NeRF, right? Think of it this way. Rather than storing the coefficients to these spherical harmonics, which is like a fixed equation that you can just evaluate, they're basically saving a little tiny NeRF right here, a 2-layer multi-layer perceptron, and then they basically put in the view direction, right? So they put in, where are you looking at this from? Here. FI base contains base RGB color. FI dir and FI time encode information related to view direction and time. And then they basically feed that into a little MLP, and that's how you get your final color, which is effectively a nerf, right? Like, that's basically a nerf. What a nerf is you're basically saying, here's the position in space, and then here's the view angle that I'm looking at it. What is the color and opacity of that? Right? But the problem with that is that now you have to perform inference on this little multi-layer perceptron anywhere that you want to ask that question. So here they do that exact same trick. They're basically saying, hey, rather than storing these spherical harmonic coefficients and then having that basically that color and the view direction or the view dependent nature of that color being stored within those spherical harmonic coefficients, why don't we just have this little multi-layer perceptron and we can query it with a specific position and time and view angle, and then it'll give us the color at the end of that. So here they say, since the MLP network is shallow and narrow, our method still achieves fast rendering speed. But I'm like, dude, you're just coping. This is like some copium here, right? Like, the reason nerfs are super slow is that you have a little multi-layer perceptron like this that you have to evaluate. So they literally just made a nerf. So this paper is a little bit weird like that. It's basically a Gaussian splat where they store the view-dependent stuff in a nerf, this little MLP. Okay. But the main meat of this paper is really how are they going to do the deformation, right? This moving 3D Gaussians. How are they going to basically create motion within a set of Gaussian splats, right? Like, how are they going to add Gaussian splats that can appear and disappear, right? So like this guy here with the flamethrower, like you see these little splats here that represent the fire, right? Like, depending on where you are in this video, those splats are basically either there or they're not there, right? So like the opacity is changing over time, right? And the position of those Gaussian splats is probably also changing over time. So how are you going to do that? And the way that they do that is they add basically temporal opacity and then a polynomial trajectory and a polynomial rotation. Okay, so we go here to the method section. We propose a novel representation based on space-time Gaussians. Our approach takes multi-view videos and creates 6-stop videos that allow for rendering in novel views. Okay, so it's basically like a Gaussian splat, but with the time dimension. Sorry. To represent 4D dynamics, we propose space-time Gaussians that combine 3D Gaussians with temporal components to model emerging and vanishing content, as well as motion and deformation. Specifically, we introduce a temporal radial basis function to encode temporal opacity, and then which can effectively model scene content that emerges or vanishes. So basically the opacity, which is the kind of see-throughness of the Gaussian, it can change over time, right? So it can basically be completely see-through and then it goes not see-through at all and then completely see-through again, right? And then that's how they're going to kind of deal with the things that appear or disappear. And then they're also going to have this time-conditioned parametric functions for the position and rotation, which is basically time-conditioned parametric functions just basically means functions that you plug in the time and then they'll give you the position, right? And they're going to use a polynomial for that. The opacity of a space-time Gaussian is this, and the temporal radial basis function. So radial basis function is actually kind of like a little bit of a reference to RBF. Like this was if you might have heard of RBF kernels, which is pretty old, ancient machine learning stuff. But it's basically a function where you're defining it with respect to some center point, right? And the radial there refers to the fact that it's like a distance to a center point. But here it's kind of a little bit overkill because the whole like radial part of the radial basis function is usually because it's kind of like a multi-dimensional function. So you're describing some vector in a multi-dimensional space and you have the radial distance to that multi-dimensional point, right? But here it's literally just a one-dimensional Gaussian. So I feel like it's a little bit overkill calling it a radial basis function. They should just called it a fucking 1D Gaussian. But basically they have a 1D Gaussian with some center in time, right? So some temporal center. And then here's the time. So you're evaluating what is the see-throughness of this Gaussian at time step t. So you're plugging in the time step t. Then there's some center time, which is when the Gaussian is brightest or most not see-through. Then you have some kind of scaling factor to make it more wide or less wide, kind of like the variance, right? This is almost looks like a little Gaussian here, exponent. And I think this picture makes it look the most obvious. So you have your opacity, which is the see-throughness, this little sigma here. You have time, right? So the start of the video and then the end of the video. And then you're basically saying, okay, I'm going to have a one-dimensional Gaussian, and that one-dimensional Gaussian is going to have some center, some position, and some scale. And then when I just evaluate this Gaussian, and here it's very see-through, here it's not see-through, and then here it's very see-through. So if there's a point that basically is permanently on, right? If you have a little Gaussian splat that never becomes see-through, then you would basically, this Gaussian would just get spread out. It would have a huge kind of spread, and then it would basically just be very, very high the entire time. If you have a Gaussian that only becomes see-through at the very, very end, then you would basically imagine just shifting that little Gaussian over like that, and then you would just have like a peak. So the one-dimensional Gaussian is a kind of it does have some amount of inductive kind of biases there, where it's like going up and then back down, but you can kind of compress it and move it and shift it around such that you can get kind of the pattern that you want for temporal opacity. Right? So now, for each little Gaussian splat, rather than storing a single opacity, you're now going to store a couple things. You're going to be storing this sigma is, you're going to be storing this sigma I, or si tau, and then you're also going to be storing this mu I tau. So you kind of, to get the time-dependent opacity, you now have to, rather than store a single opacity, which is what you have in these kind of like static Gaussian splats, right, now you have to store 3 numbers, which are going to basically parameterize this little equation here, this radial basis function, which is then going to allow you to basically plug in for any time t and get the opacity of that specific little Gaussian. Okay, and similarly, they're going to basically do the same thing for motion. So in order to get motion for a little Gaussian, give the Gaussian some ability to kind of rotate and move over time, they're going to use a polynomial. So a polynomial, the polynomial there just refers to, you guys have definitely seen this before, but you see this k here. So you're taking this term here, and then you're raising it to the k power, and then you're going from k equals 0 to np. And np is the polynomial kind of power, and it goes up to 3. So basically this is like something something plus something something x plus something something x squared plus something something x to the third, right? That's kind of a polynomial. So what they're basically saying is that the motion of any of these, the trajectory of any of these little space-time Gaussians can be basically some kind of third degree, like kind of like a spline, if you want to think of it that way. So that does have its, much like this one here, right? It has its own kind of biases, right? Imagine if you had a trajectory that was more complicated than that, right? Where like something like almost like teleported or like, or maybe like vibrated or something like that, right? Like you're not going to be able to encompass that kind of complicated trajectory with a polynomial, but for 90% of use cases, the polynomial is going to be pretty good. And they even have a kind of a little sentence here that says, if you combine the polynomial motion trajectory with the fact that you have this ability to kind of fade in and out, where it's like getting see-through and then more see-through and then less see-through and then more see-through. So like if you combine those two, you can get a good balance between representation capacity and model size. So you can get kind of the effects that you want with these two kind of things. And much like here, where by adding this time dimension now for each little Gaussian, you have to store the mean and the scale of the Gaussian, the one-dimensional Gaussian for the opacity. There's a similar thing here, where now rather than just storing 3 numbers that represent the center of this little Gaussian splat, you're going to have to store all this shit here. You're going to have to store these BIKs, you're going to have to store this KPs, so you're going to have to store all this extra crap. But that's what you do when you're doing 4-dimensional Gaussians, right? It's basically you're just adding a bunch of extra parameters to each of the little Gaussians, and really you want the smallest number of parameters, but you also kind of want to pick parameters, enough parameters that you get good quality for a specific amount of parameters. And the polynomial, they're also going to use one for the rotation. So you see here, same kind of thing. Another polynomial from k equals 0 all the way to nq. In this case, nq equals 1. So they use third-degree polynomial for the motion and then a first-degree polynomial for the rotation. So I think the quaternions really only rotate in a very simple kind of way. They probably only just do this, like whoop. We keep the scaling matrix to be time independent, so they're not going to, if they have rotation, that's kind of effectively the same thing, right? Because you're kind of like rotating it. And that's that. That's how they add basically movement into the Gaussian splat. So basically every single one of these little Gaussian splats now also has some trajectory in time, and also has basically a temporal opacity, so it fades in and out. And they do, this is the, so this trick here, this is the, I think we literally just went over this, but this is basically another weird little trick that they had here, where they basically use a little multi-layer perceptron to basically store or get the view-dependent effects on the color instead of using the spherical harmonics. I feel like this is just like, why put this in this paper? Just make that a separate paper. Like, I don't know why they needed to add that. But the other thing they add here, which is what this figure is about, is that they add an extra sampling strategy. So whenever you're creating these Gaussian splats, it's an iterative technique where you're basically adding and removing Gaussians, right? So you initialize the scene and you have whatever 2 million Gaussians, but then over the course, right, you might remove some Gaussians. So you might notice that some of these Gaussians are just in the corner and they're never really receiving any gradients. They're not moving very much. They're all kind of, you just delete them. And then maybe you notice over here in this part of the Gaussian splat, there seems to be Gaussians that move around a lot, that are kind of trying to model too many different things. So let's add more Gaussians there, right? So when you're creating these Gaussian splats, you're adding and removing points over the course of this iterative process of optimization. So here they have their own kind of little secret sauce where basically they sample new Gaussians along rays by leveraging the guidance of training error and course depth. And this is just like a fancy way of saying that they're going to be looking at the scene, and then over the course of optimization, you're going to have specific parts of the scene where the error is really high, right? Which basically means that the Gaussians there are there's not enough Gaussians, there's too many Gaussians, they're not sampling correctly. Here it's like there's not enough Gaussians. So in those area of high error, you're going to basically add more Gaussians. So just another kind of seemingly unrelated little trick that they jam into this paper, which I feel like already had too many things to begin with, but it's basically just a way of getting adding more Gaussians. We sample new Gaussians along the ray of pixels that have large errors. We patchwise aggregate the training errors to prioritize on areas with substantial errors rather than outlier pixels. We sample a ray from the center pixel of each selected patches. New Gaussians are then uniformly sampled within the depth range along the rays. Okay. Question from SHZ: what will replace the mouse in 3D? It'll be speech. You'll just be able to talk, and then you'll also, the eye tracking is also pretty good, so you'll be able to look. And then eventually all of it gets replaced by BCI, which is brain computer interfaces, right? So eventually the combination of eye tracking and then the brain computer interface, which is basically looking at the electrical information coming out of your brain, all of that will just replace the mouse. You'll just kind of like look at things and it'll kind of infer what you want to do. Having a derivative, equation 7 is symmetric. Is quite as strong. Everything will take as long to disappear as it takes to disappear. That's a good point, Wall. Look at that. That the prior here is... Yeah, this feels to me like kind of... I don't know why they chose this 1D Gaussian as the prior for the opacity. I guess it's like... It's less parameters than like a square wave. Or like, I don't know. But I'm with you. There's something to be said about the biases that they're introducing with the choice of polynomials for the trajectories, Gaussian for the opacity, and then polynomials for the rotation. Welcome back, Nerf floaters. Yeah, Gaussians have their own kind of problem with floaters as well, but that's also what the like pruning is. So like these this process here where they're sampling and adding more Gaussians, right? There's the opposite process is basically the pruning. So you're kind of alternating these like sampling and pruning and sampling and pruning. I think sometimes the sampling is called densification. So you're densifying the Gaussians, and then pruning is also called removing or sparsifying. You're basically removing some Gaussians if you have too many of them, but that's basically it. Implementation details, NVIDIA A6000. These are the different data sets that they're testing it on. I think the videos that we saw are always kind of the best way to judge the quality of these things. They're still, seems fine. I don't know. It's hard to like complain here. It seems like theirs is a little bit more detailed. This is an interesting kind of scene, right? It's like there's a lot of weird colors here. Looks a little bit, this is the ground truth. So what is this? Looks a little bit cleaner. These are Hyperreal, Nerf Player, other types of 4Ds Gaussians. The fire one is, I think, the coolest because it has that, the fire is just such a, it's like, fire is kind of like smoke, where it's like one of those things in like 3D that is like so difficult to like model correctly, right? It's like fire is something that is like very bright. It's also kind of, it has like some notion of view dependence. It's also disappears, reappears. Like there's a lot of cool shit. If you can render fire, you can pretty much render anything. Temporal opacity. Some ablation studies. Our method outperforms Nerf Player and Hyperreal in both speed and quality. 10 times faster. The peak signal to noise ratio, LPIPs, and the structural similarity image matching index. I don't exactly know, but these are basically quantitative metrics of image quality. Improvements are significant. Limitations. Although our representation achieves fast rendering speed, it cannot be trained on the fly. The support for on-the-fly training could benefit numerous streaming applications. To achieve this, advanced initialization techniques could be explored to accelerate the training process or alleviate the requirement of per-scene training. On the other hand, our method currently focuses on multi-view video inputs, in this promising to adapt our approach to monocular setting by combining with regularization or generative priors. Yeah, so here they're saying that the video, the scenes that they're using are these specific scenes that people created for the purpose of basically benchmarking these Gaussians and these space-time Gaussians and space-time Nerfs and things like that. But these are multi-view scenes, right? So basically every single one of these scenes, there's really like 4 cameras or even more than that videotaping at the same time, and someone calibrated the cameras, they sync the cameras. So you're not going to have access to that. So ideally, you want to be able to create these space-time Gaussians with just a single camera, right? You want to be able to create this with just like the camera on the rabbit, right? There's just one camera there, right? You don't have multi-view. So you want to get to the point where you can use just a monocular camera to generate these types of scenes. Generative priors, you see that? It's the magic, dude. Now we're talking Dream Gaussian, right? Which is the using two-dimensional image diffusion models like Stable Diffusion to basically create 3D objects. Conclusion. We present a novel representation based on spacetime Gaussians. The proposed spacetime Gaussians are enhanced with temporal opacity and parametric motion and rotation to model complex 4D content. To increase model compactness and encode view and time-dependent appearance, we introduce the splatted feature rendering, which is this little tiny, it's basically a Nerf. Additionally, we leverage guided sampling of Gaussians to further improve the rendering quality. This is the extra little trick. So these 2 extra little tricks that they have there, I feel like they could have just not had those and then just put those in separate papers, but they really wanted to kind of really pack everything in. Experiments on real-world data sets show that our representation delivers state-of-the-art quality at high resolution and FPS while maintaining a compact model size. Cool beans. The person who produces... What's going on here? Who produces the foundation model will end up like Prometheus and change to a rock for eternity? I don't know about that. Can't be interactive and open-ended physics. Consolidate or cluster of splats. So Jay, to answer your question, yeah, with these Gaussian splats, right, it's basically just set collections of these little splats. But over the course of the splat creation process, right, when you're creating these Gaussian splat scenes, you're removing and adding splats. So you're basically adding splats and then removing splats. And there's a lot of different ways to do that, right? You can say, for example, okay, well, if there's a lot of splats that are kind of moving into this area, then add more splats. If there's this area here that doesn't have any splats, then, or that just has one splat that's just kind of sitting there not doing anything, then remove that splat. So there's a lot of different heuristics that you see in these splat papers for adding and removing splats. This is just one random densification technique that they use in this particular paper, but there's nothing magic about this one. There's like a billion other ways to do that. Okay. That's basically it. I was going to review this paper too. So this paper was in the title as well. This one, Amortized Generative 3D Gaussians for Single Image to 3D, but I was like reading it, and then I like looked at the results, and it was like it's pretty much just like the same shit tier quality as everything else. So like it's not state of the art. They didn't get good results. It's like I don't know. It seemed just like not good. It's also extremely complicated. Like it's just like 20 different things all just like glued together to try to get to this point that isn't even good. So I don't know. I felt like these other papers were just way cooler, so I focused on those. So a little bit of a letdown on that one, but these were cool. Compact 3D was cool, and then Langsplat was very cool. So that's pretty much it, guys. Let me drink this coffee if you guys have any questions, and you don't even need to keep it relevant. Feel free to ask whatever questions you want. It seems like you guys want me to be like George Hotz and just rant about politics or something. I don't know. I don't have any good political opinions. I don't think anybody's political opinions are good, actually. My hairline receded a little with the last GitHub repo they produced. I mean, you just join the shaved club. I'm telling you, it's so much easier. You don't have to pay any money. I've been cutting my hair for years. Rant about physics instead. I think a lot of physics might be wrong because there's this kind of assumption that the emissivity and basically the speed of light being constant everywhere in the universe, like the more I think about that, I don't feel like that's a good assumption, right? Vision Pro February launch, what's the expectation? The Vision Pro is good from what people say, but it's also just like way too expensive. Like it's like a $4,000 headset. Like what the fuck are you doing? Like no one's going to buy that. So I think that it looks good now, but like compared to the Quest headsets, like you're not going to see enough volume for games to really appear. I think the Quest headset is still going to be the dominant headset, but I think Apple is smart, right? I think Apple's kind of doing the Tesla strategy where it's like, don't try to make like the mass market thing, make like a luxury thing. So if you make the luxury thing, like the luxury car or the luxury VR headset, you only have to do low volume kind of manufacturing, so it's easier. But then also it has this kind of like consumerism effect where it becomes a luxury product, right? So because Tesla created basically expensive cars first and then went down towards the cheap cars, you had a notion of the Tesla car being a status symbol, right? So now even when someone goes and they buy that like $30,000 Tesla, which is just a consumer car, like they feel like it's a fancy car. So I think Apple's kind of going the same way. They're like, hey, let's make a $3,000 VR headset. No one's going to be able to buy this, but you're going to see one or two at the airport, or like maybe you go to your work and someone has one, and it's going to feel like a status symbol, and then we kind of bring the price down over time. So it's generally a pretty good strategy when you're making things like that. Kind of the opposite of this. This is like you're hoping that people just impulse buy because they're going to get it, and then they're going to play with it. They're going to realize it's pretty shit, and then they're never going to buy it again. So kind of the opposite approach. I think going that opposite technique and doing something that makes it a luxury product and then go down, I think that's a better strat. CES 2024. I don't know much about CES 2024. I didn't go. I've never really gone, but it seems like they just released a bunch of like stuff, cool TVs, EVs. I don't know. Few rants about rotation. Rotors seem better than quaternions. Rotation in general is a mess. Is rotation even real? Yes. Quaternions are the best way to represent rotation because it's full. The worst way to represent rotation is Euler angles, which is 3 numbers, but you can basically have the gimbal lock and a bunch of other problems. It's like underparameterized. Rotation matrices are the best, but it's 9 numbers, so it's a lot to deal with. So quaternions are kind of in between. They're 4 numbers, and that's why I like them the best. Okay. Let's summarize this, and then I'll give you guys time here. So today, we reviewed a bunch of different Gaussian splatting papers, specifically Langsplat, Compact 3D, and Spacetime Gaussians. So these are different papers. They're in different kind of areas, but we're just reviewing them because it's been a while since we reviewed some Gaussian splatting papers, so we're interested to see where the community is at right now. So starting with Langsplat. Langsplat is basically adding the semantic clip features to Gaussian splats. So the TLDR of this paper is they basically use the segment anything model, which is a pre-trained segmentation model from Facebook that is also open vocabulary. So you can basically, it's not limited to some predefined set of categories. And they feed their multi-view images of some scene, which is what you have when you are creating a Gaussian splat, right? You create it from these multi-view images. And you feed each of those into the segment anything model. The segment anything model, not only does it segment things, but it also segments things in a way where you get this kind of hierarchy of parts. So it'll basically segment out here for a point query, you get kind of the largest part, which is the person, then the backpack, and then the zipper on the backpack, or the emu, and then the top half of the emu, and then the head of the emu, right? So they leverage the segmentation power of segment anything model in order to get these 3 kind of whole parts and subparts masks. Then they feed only that specific part into clip. So clip will give you basically a feature vector which represents the semantic, or kind of, you could think of it like the text of that specific thing, but they make sure to use these segmentation masks because they don't want the stuff around it, right? They don't want the like table and the chair and the background. They really only want this sheep, right? So then they get basically these 512 dimensional clip vectors, 512 dimensional clip features for each of those, right? So they have 3 of those. And really, that could be the end of the paper, where, okay, well, now we basically have clip features for every single one of our little Gaussian splats, and if you want to open vocabulary query your 3D scene, right, if you want to be able to say, okay, well, what is the spoon, right, then you can basically just use simple kind of filtering like this with a relevancy score and find the specific Gaussians that are the most similar to that text query that you had. But the problem that they run into is that whenever your scene, your Gaussian scene is composed of 2 million Gaussian splats, right, adding an additional 512 dimensional clip features, not just 1, but 3 for each of the 3 levels of hierarchy, explodes the total memory footprint of your Gaussian splat. So in order to compress down this 512 dimensional clip features, they create a image encoder, or an encoder and decoder, not image encoder. This encoder, all it's encoding is it's encoding this 512 dimensional clip feature vector into a 3-dimensional, kind of basically think of it like a little mini clip feature vector, and then that is what is being stored with each of the Gaussians. So each of the Gaussians basically now has a little mini 3-dimensional semantic little feature vector that if you ever want to know what this Gaussian is, you can basically just take that little feature vector, feed it into the decoder, and you'll get a clip vector, and then now you can use that clip vector to know that that is the nose of the bear. And that's basically it. Pretty cool. I think this has a lot of interesting applications in things like robotics and VR, AR. I think that querying, open vocabulary querying of 3D scenes is incredibly powerful, and we're going to basically need to have that for robotics and AR, VR, especially robotics that use or that plan in the space of language, right? I think that's kind of something that we see coming in the pipeline. And if your robot is planning in the space of language and having kind of an internal chain of thought that is like, I should grab the spoon. Where is the spoon? Being able to query its environment and find the specific Gaussian splats with their little centroids and positions, right? That's going to be super useful. So that is LangSplat. And LangSplat, one of the problems that I ran into, right, which I was saying was this 512 dimensional feature vector that they had to compress to 3-dimensional feature vector. They did that because they were running out of space. So that transition leads us to this paper here, Compact 3D. Compressing Gaussian splat radiance field models with vector quantization. This paper was about taking Gaussian splats and basically creating a code book. So the VQ vector quantization, very similar to the VQ in a VQ VAE, where basically rather than storing the same information explicitly, most notably, for example, the color for every single Gaussian splat, instead you're going to create this code book. And this code book is basically going to contain, for example, the yellow color of the Wall-E robot here, right? So rather than storing that yellow color 10,000 times in 10,000 different Gaussians, or 10 different little Gaussian splats, you can basically just store it once in this code book, and then in your Gaussian splat, all you store is basically the index to that particular color in this code book. So they trained this code book in tandem with the Gaussian splat itself so that you can kind of make sure to really only keep the things that you care about, and they get pretty much a 20x reduction in size by doing that, which is pretty good. And it seems like the quality is not terribly impacted. Obviously, you're going to lose some amount of information, but mostly it seems like you got pretty much the same quality Gaussian with 10 times less amount of memory, which is pretty good. And yeah, you wish they would have done it for this paper, right? That would have been very useful, because I think a lot of these clip feature vectors are probably repeated within the image. And then finally, the last paper that we looked at was this one here, Space-Time Gaussian Feature Splatting for Real-Time Dynamic View Synthesis. And this is a Gaussian splatting paper where they're trying to basically add the time dimension. So they're really trying to basically create these, rather than static 3D Gaussian scenes, they're trying to create these kind of like Gaussian videos, right? And in order to do that, you're going to need to add the ability to basically emerge and vanish and then move and deform. So these Gaussians are going to have to be able to move, right, throughout the scene over time, and they're also going to have to be able to basically emerge and vanish, which is done by changing the opacity, right? The opacity is a very common parameter that is used in Gaussians. It's basically how see-through it is, right? And it's very important because whenever you're rendering a Gaussian, you're doing this tile-based kind of sorting, and then you're basically adding up these opacities. So the opacity kind of, that see-throughness is important for the final color in the image. So they're going to have, rather than, for example, the opacity being represented by a single number for each Gaussian, they're going to represent it as 3 numbers, and those 3 numbers basically parameterize a one-dimensional Gaussian, which they kind of like overkill describe as a radial basis function, but really it's just a 1D Gaussian in time that basically, whenever it's 0 opacity, it's see-through. Whenever it's at its peak, it's fully visible, right? Not see-through. And then at the very bottom, it's see-through. So it's basically, you can imagine every single Gaussian has some changing opacity or temporal opacity, which is a function of time. So you're also going to need functions of time to describe the motion in terms of the XYZ kind of trajectory, and then also the rotation. And for the XYZ motion and the rotation, they're going to be using polynomials. So basically polynomials up until order 3, so to the 3rd power here. So that's a spline. And then for the rotation, it's to the NQ equals 1, which is basically just a 1D, which is just rotating 1D. But that just changes, right? So now rather than storing the 3 numbers that you would need for the center of the Gaussian in a static 3D Gaussian scene, now you're storing all these extra numbers here, which are basically the coefficients to your polynomial function, as well as this number here. So basically, you're adding extra parameters to your Gaussian splat collection of Gaussian splats. So rather than each Gaussian splat just having some limited set of parameters like this, you're basically adding some extra parameters, but those extra parameters allow you to create these Gaussian splats that are basically videos, right? So you can add and change Gaussians over time. So here, for example, this view, they show you the center of the Gaussian, so they get rid of basically the spread. So now you can really see the trajectory that each of these individual Gaussians that is representing the fire is doing. You can see how some of them fade in and out, some of them kind of move. Pretty cool. What else? And then there's two other extra tricks in this paper that I guess are worth noting. One trick that they do is kind of using the training error to identify areas where you could add more Gaussians. So they call this guided sampling strategy. So basically a densification strategy for Gaussian splatting, where you basically add more Gaussians in areas where your error is high. And then another little trick that they do, which I think is fucking weird, but they replace the spherical harmonics, which is a way of basically storing view-dependent effects, kind of using spherical harmonics, which can be evaluated kind of explicitly. Rather than doing that with the spherical harmonics, which is what most people do, they basically create a little nerf. They create this little MLP phi here, which they can feed in these particular view direction, and it'll give them the final color. And that is effectively a nerf inside a Gaussian splat. So kind of weird, right? Because it literally removes the benefit of the Gaussian splats, because now you're going to basically have to evaluate this little multi-layer perceptron for every little Gaussian splat in order to get the final color. So I don't know. It just seems like you're losing the advantage of the Gaussian splats, even if this MLP network is shallow and narrow, right? You're still going to need to evaluate it a huge amount of times in order to get that final view-dependent color. That's basically it, guys. 3 papers, 3 kind of different directions that people are taking Gaussian splats, but so far so good. You know, it seems like we're getting better at compressing these Gaussian splats. We're getting closer and closer to kind of 4-dimensional Gaussian splats, like Gaussian splat videos. And then we're also kind of seeing that you can add basically semantic information to these splats to do very interesting stuff like open vocabulary segmentation. So splats are nicely chugging along. All right. Any other last questions here? Looked how humans constructed the world and theorized it would be like in 30. Wonder if that's too many features. Maybe. I don't know. Okay. I think I'll end it there, but I appreciate everybody listening. Hopefully you got something interesting out of this. Thank you, Jay87, Spyro, Josh, Ed, SHZ, who else? Wall, Eris, Chris, SHZ, I already said Chris. Scrolling up here. I'm trying to make sure I get everybody. Nuno, Liu. All right, I think that's everybody, but thanks for the stream. Hope you guys got something out of it, and have a great weekend.